All right, here is iChem Lesson 21, your second to last iChem lesson of the semester. Make sure you are taking notes through all of the example problems, especially so you're prepared to complete similar calculations on your own tomorrow. So the first thing that you need to learn is this KW value. Without going into too much detail, this KW is considered an equilibrium constant for the reaction of water dissociating into its ions. You'll find the reaction at the top of your notes with the water molecules dissociate into the ions. This KW is the ratio of the products, the ions, to the reactants. This ratio is always going to be the same for water. So we can use this if we know one concentration to calculate the other, and we can also use that information to decide whether the solution is an acid or a base. Because we know that acids produce hydrogen ions when they dissolve in water, we know that the hydrogen ion concentration will have to increase. If the hydrogen ion increases to keep that equilibrium constant, the hydronium ion will then decrease. The acids are characterized then by having a higher hydronium ion concentration than hydroxide ion concentration. The reverse is true for bases. Bases produce a hydroxide ion when they dissolve in water. So when you dissolve a base in the water, the hydroxide ion concentration is going to increase, thus the hydronium ion concentration will decrease, and bases are defined by a hydroxide ion concentration greater than the hydronium ion concentration. Now let's put this knowledge to work. We want to know what the concentration of hydroxide ions in saturated lime water if the hydronium ion concentration is 3.98 times 10 to the negative 4. Anytime you have a problem that involves finding one ion concentration from the other, you use this KW equation to solve it. So we know KW is 1 times 10 to the negative 14, equal to the hydronium ion concentration, which is given, times the hydroxide ion concentration. I forgot to say on the previous slide, but these brackets in the equation mean concentration. So if you see brackets around hydronium ion, you're talking about the concentration in molarity. Both of these are molarities. Okay, so to find hydroxide ion concentration, I need to divide both sides by 8.9. That's not an 8. 3.98 times 10 to the negative 13. So be careful here. It's a couple of options. If you have the button on your calculator, you're going to want to use the capital E if you remember that from before. If you choose to not do this, make sure while you're plugging in you put parentheses around this whole number so the calculator does the appropriate order of reactions. You should get a hydroxide ion concentration of 0.026. The units of concentration are molar. Okay, we need to decide whether this is an acid, base, or neutral. I need to compare the concentrations. So the concentration of the hydronium ion, this negative 13 here means that there's actually, that the decimal place is moved to the right 13 times to write this. So what it really means is 0.0000012 total zeros until you get to 398. So this is a really small number, whereas this is still still a small number, but a relatively large number. So the hydroxide ion concentration is greater than the hydronium ion concentration. So this is a base. Let's do it one more time. You want to know what the hydronium ion concentration is given the hydroxide ion concentration. Again, 1 times 10 to the negative 14th equals hydronium ion concentration, which is what I'm looking for, times the hydroxide ion concentration, which is given as 1 times 10 to the negative 8th. To find the hydronium ion concentration, I divide both sides by 1 times 10 to the negative 8th. Being careful with order of operations in my calculator, I get 1 times 10 to the negative 6th molar. I need to compare these two numbers to decide if it's an acid or a base. The hydronium ion concentration as times 10 to the negative 6th, or the hydroxide is times 10 to the negative 8th. The bigger the negative number in the exponent, the smaller the number. So the hydronium ion concentration is greater than the hydroxide ion concentration. So this is an acid. Now moving on to what you guys all know to be associated with acids and base is the concept of pH. The pH scale measures how acidic or basic a substance is. It ranges from 0 to 14. A pH of 7 is considered to be neutral. A pH less than 7 is considered to be acidic or an acid. pH greater than 7 is considered to be basic. But what does pH really mean? If we look at this scale for a minute, we can see that as the pH goes up by 1, the concentration of hydrogen ion decreases 10 times. pH of 0, the hydrogen ion concentration is 1. pH of 1 is 0.1. pH of 2, 0.02. Every pH is a 1 move of the decimal point over to be a smaller and smaller and smaller number. We can represent this just by adding zeros before the 1 after the decimal point. You'll notice that a pH of 0 is a much higher hydrogen ion concentration than, say, a pH of 8 or 14. Right? We know that pH of 0 would be an acid, and we also know that an acid should have a higher hydrogen ion concentration than something like we know to be a base. pH of 14 has a really, really low hydrogen ion concentration. These numbers here are messy, especially when you get to the really, really, really small numbers. So that's why the scale of pH was created. It's a easier scale to deal with, but still at a glance tells you the hydrogen ion concentration in a way. We can look at the scientific notation. We can see that pH of 1 is times 10 to the negative 1, pH of 2 times 10 to the negative 2, 3 times 10 to the negative 3, and so on as you go through. This again shows you that every increase of pH is a 10 times smaller of a number. And the higher the pH, the lower the concentration of hydrogen ion. The way we apply this mathematically is using logs. Unfortunately, those of you who are juniors probably haven't taken the math class where you learned what logs mean, but now that you understand the relationship between concentration and pH is that 10 times relationship, we can just really plug it into the calculator. Button on your calculator, you should have a button that says LOG. That's what you use to do this math. So its pH is defined as the negative log of the hydrogen ion or hydronium ion concentration. We learned to calculate these concentrations using kW. Therefore, a pH problem could give you the hydrogen ion concentration directly or the hydroxide ion concentration and expect you to do that calculation first. So pay attention to which concentration you're given. Let's do a few examples. Here's the first example. You have a sample of maple syrup with a hydroxide ion concentration of 5.0 times 10 to the negative 8. You want to know the pH of this solution. Okay, let's pull up the definition of pH. pH equals minus log of the hydrogen ion concentration. We also know that 1 times 10 to the negative 14 equals the hydronium ion concentration times the hydroxide ion concentration. So first, I want to plug this into here to solve for this, and plug that into there. So 1 times 10 to the negative 14th equals hydronium ion concentration times 5 times 10 to the negative 8th. Hydronium ion concentration equals 2 times 10 to the negative 7 after I divide both sides by 5 times 10 to the negative 8. And then I plug this into my pH equation. pH equals minus log 2 times 10 to the negative 7. I end up with a pH of 6.7. This is less than 7. You could consider this to be acidic, slightly acidic maybe. A lot of people also would just consider this to be close enough to neutral. Depends on the situation, how precise you need to be. Alright, one more example. This time, I'm given the hydronium ion concentration, which is the same as my hydroxide ion concentration. So I have this equation. All I need to do is plug that number in. Minus log 2.51 times 10 to the negative 5. Pay attention, make sure you put both of those negatives in there. They will certainly matter on what you get for your answer. You should get a number between 0 and 14, and it should be a positive number. If you don't get either of those things, then you put it into your calculator incorrectly. 4.6. That is acidic. It is less than 7. There's one other little guy you need to learn about, and that's pH's little sister, pOH. By the same way we can define pH as a minus log of the hydrogen ion concentration, we can define pOH as a minus log of the hydroxide ion concentration. Based on the KW and what we know about the two concentrations, the log versions of the concentrations, the pH and the pOH, would add up to 14. So if you're given a pOH, it is so easy to find pH. pH equals 14 minus pOH, if I rearrange that equation. So for the first one, A, pH equals 14 minus 4.32, which is equal to 9.68. B, pH equals 14 minus 8.90, which is equal to 5.1. Easy as pie. Based on all of these relationships, you only have to be given one value, one ion concentration, and from that you should be able to calculate the other ion, the pH, and the pOH. I'm going to do one example for you and expect that you do the other one. Alright, so first I'm given H+. First thing I can do, apply KW. To find hydroxide ion concentration. So the hydronium ion concentration is the same as hydrogen ion, and I'm trying to find hydroxide ion concentration. I divide both sides by 4.29 times 10 to the negative 11. I end up with hydroxide ion concentration, apologize for the noise outside my door, of 2.33 times 10